Hey guys, take a look at this. You probably didn't know, but I have a side of power electronics. More than 15 years ago, I was there in the 4HV forum, developing and appreciating the just new double resonant solid-state Tesla coil. I was very young at that time and it was one of my first big challenges on electronics. Look at this, this is a young Gregory in a Faraday cage in his parents' house yard. At that time, I designed a lot of different Tesla coils using different topologies, different modulators, learning a lot with the big guys, Steve Howard, Steve Corner, Eric Goodshield. After some time, I designed probably one of the largest Tesla coils of the world. It was a moving Tesla coil that was used in the carnival party in Brazil. I used 2 diesel generators to power this machine, and the biggest challenge there was the grounding. So in this video, we are going to the whiteboard and we are going to learn how a modern Tesla coil works, how all this power electronic stuff behaves, how a Tesla coil is related to the problem of impedance matching, and in the end we are going to see how a PFC I made worked, running 4 parallel boosts, 4 phases, translating the mains power to a 600 volt bus to power the Tesla coil inverter while delivering 15,000 watts. This is a very special video for me because I never talked public about my Tesla coils, and I hope you enjoy. Take your coffee and come with me. Let's begin this video from the end result, from the spark, and we're gonna go backwards to understand how the overall Tesla coil, how the overall modern Tesla coil works. So here I draw my Tesla coil, my old Tesla coil, one of my old Tesla coils looked exactly like this. Here we see some very important aspects of a Tesla coil. We have this toroidal shape here that's made of aluminum tube. We have the secondary coil that's a long inductor made of a copper wire. We have in green the primary winding, primary coil. So this we call top load, secondary, primary. And what is the big end result of a Tesla coil? The objective of the Tesla coil is to generate very big sparks. So the output, the goal of the Tesla coil is to generate very high output sparks. Sometimes the sparks touch the ground and it becomes very thick with a higher brightness because the current here increases when it touches the ground. We always need to draw the ground line. So the end goal is to generate this very high brightness, very loud sparks that can go 3 to 4 to 5 meters, 4.5 meters of distance. First of all, what is this spark here? This spark here is a very high voltage and high current discharge. The Tesla coil, the circuit of the Tesla coil is behaving in a way that is charging this top load with a very high voltage. This top load here is actually a capacitor of the circuit. So actually here we have capacitance to the ground, C2. The capacitance of the secondary side, as you're gonna see. So now you understand why we need this tubular section in the top, why it is round, and why it is metallic. It is metallic because it behaves like a plate of a capacitor, where the other plate is the ground. It is large to increase the surface area, to increase the capacitance, and it needs to be round to prevent the energy, the high voltage leaking, to prevent small sparks leaking in corners of the structure. This is why it's round. So what's happening here is that the voltage of this capacitor here is increasing a lot up to the point it is sufficient to break the dielectric capability, the dielectric insulation of the air. So here we place a small wire to create a very controlled leak point here. And when the voltage here is higher enough, it breaks the air and we have the discharge of this capacitor to the air, creating these very strong sparks. And this is a very important topic, guys. This is a very important aspect we need to understand. Currents here on the sparks are very high. I always read someone talking about it, saying that is high voltage and low current. Because of course, people think about energy conservation, about power conservation. But a Tesla coil works in burst mode. So it accumulates energy as a high voltage over this output capacitance, and when this energy is discharged, it creates very high currents. And this is actually what we see, that very high brightness, the loudness, all this is very high energy, is current, heating the air, expanding this plasma. The plasma here is expanding the air, creating a very strong sound wave that we hear. So always remember that the output of a Tesla coil has high voltage and also high current, because it works in burst mode. So we have the top load and the ground creating this parallel capacitance in the output of the circuit, and the secondary coil is a very big inductor. So this actually is a very big inductor that makes a resonant tank with the output capacitance. The primary coil is also an inductor, and inside the Tesla coil circuit, here inside the box, we have, before let's draw here, this inductor here, the primary here is L1, and inside here we also have a capacitor, a series capacitor. I'm gonna draw it later in the circuit as a circuit schematic. We have a series capacitor connected, going to the circuit, that is C1. So we see here that this is a double resonant circuit. We have two resonant circuits, the first one created by C1 and L1, and in the secondary side L2 and C2. This is why this is called a DRSSTC, a double resonance solid state Tesla coil. And here on the all electronics family, we need to take a look at this in a different point of view, as always. So actually think with me. This is a problem of impedance matching. We have energy available in the mains, 220 volts at 50 amps, and we need to impedance match the air to this low impedance source here. The impedance here, the load impedance, if we think that this spark here is a load, it is a load, but it's a non-linear load. But let's talk here that this is a load. This is a very high impedance load. Here we have 200,000 volts, 150,000 volts. This side of the circuit is a high impedance, and we have energy available in a low impedance form. Already talked here on the channel, you can take a look on the impedance matching videos, that energy and power can be represented by different ratios of current and voltage. And impedance matching is this problem of transforming the voltage and current profiles to a different current and voltage profile that better excites the load, that better generates the goal we need to generate. Actually, the two resonant tanks are coupled together through the mutual inductance between the two coils here. We're gonna understand it in a moment. And it has this physical construction, because here we are not talking only about electronics, we also are talking about physics, in the sense that we need to take care in the construction, because if not, the system breaks apart. We have leakage sparks that come out and burn the secondary, so we have a physical problems here also. This is why it has this construction. But from an electronics perspective, it works as a bandpass matching, impedance matching filter. We have a low impedance side here, where we have the driver. The driver here is taking DC power, 600 volts DC at around 15 amps. This is generated by a PFC boost architecture that we're going to understand later. And we have the driver here that is a low impedance voltage mode driver. Is a very big H-bridge made with transistors of this size here. This is an IGBT module, and this driver here is a voltage mode H-bridge that is converting the DC level here to AC in the frequency of the resonant tank, in the frequency of the impedance matching network that we have here. So here we have square wave voltage, and as this is a bandpass structure, right, we have a series resonance here and parallel resonance here. The current here is primarily sinusoidal, right? Because the impedance is lower only at the fundamental frequency of the square wave. And this is very important, as you're gonna see, because we use this fact here to feed back the inverter and also to make zero crossing switching, reducing the losses at the transistor. This current here is 1500 amps, 1,500 amps that we are pumping in the primary of the Tesla coil here. So if we don't design it correctly, and if it was not working in burst mode, in bursts, it would actually explode. In the output of the driver here, we have 600 V peak, 1500 amps. And this actually works in the burst. So what this means? It means that it's turned off, it excites the tank for a period of time, and it goes off. Current here in the tank starts small and increases until the voltage is enough to break the air. When the dielectric condition of the air breaks, this resistance becomes very slow and we damp all the energy stored in situ into the air, creating this spark. So at the end of the burst here, the current drops a lot because near this moment here, all the energy is transferred from the primary tuned circuit to the secondary tuned circuit. Voltage is very high and the dielectric condition of the air is broken. And this peak here is 1500 amps. This frequency here is, for this Tesla coil I'm drawing here, it was 45 kilohertz. These transistors here were switching 1500 amps at 45 kilohertz. And actually the noise that we hear, the noise is not this frequency here. The noise of the Tesla coil we hear is actually the frequency, the repetition rate of the burst. So like if we are running 200 bursts per second, we are going to break the air 200 times per second and we're gonna hear a 200 hertz tone. And this is actually how music is modulated in a Tesla coil. So we have this very low impedance voltage source driving a very low impedance point here on the network, and this bandpass impedance matching network is transforming the impedance of the energy pumped to a much higher impedance where we have a much higher voltage. So this is a much higher impedance in the output here. Okay, but you may ask me, Greg, here we have transformer action, right? We have a transformation. This is not exactly what we are seeing here on the picture, on the drawing, of course, but from the electronic perspective, it doesn't matter. This topology here can be transformed to this topology here. This is a topology more useful for analysis, and this is a topology useful for construction. You are seeing the difference? Like, imagine constructing this. How you would connect this point at this point here? Impossible, right? So this topology here can be transformed. It behaves exactly equal to the other topology. Exactly equal. But now we are using transformer action to couple the two circuits, creating isolation. So this makes physical construction possible. What's very interesting here, guys, is the coupling factor. Coupling factor here is very low. In this design here, I used a conical primary. All my other Tesla coils that I made after this one, I used a planar primary coil to reduce even more the coupling factor. And you may be asking me, but a higher coupling factor is not good? Well, we reach again the physical limits of the system. We need to have a low coupling factor because we need to transfer the energy from the primary tank to the secondary tank very slowly. If we have a very tight coupling factor, energy is transferred in the first periods of the burst. Remember the burst? If we have tight coupling factor, energy is transferred too quickly, like this, and if this happens, we create sparks between the secondary and the primary. That's very interesting. We create sparks here. And this happens because we are exciting the secondary coil too quickly, and the current distribution is not a perfect linear gradient. Remember, this long structure here also have capacitances to ground. So this structure here also have capacitance to ground, the self-capacitance of the secondary coil. If we create a very strong excitation here, as the current profile is not linear, we create a very high voltage near the primary and we break here, shorting, creating a spark to the primary coil, and sometimes burning all the electronics inside the box here. C1 needs to sustain very high voltages and also very high currents. All the 1500 amps are flowing in series here. This is why the primary coil is a very thick copper coil, copper tube coil, and here this capacitor, we use a bank of capacitors. So here we have a bank of capacitors like these ones here. And in this Tesla coil, I probably use it 30 or 40 capacitors of this type here in a combination of a parallel and series to sustain the voltage here and the very high current. So this is actually a bank of capacitors, not a single capacitor, because the operational conditions here are very harsh. In the driver's side, we have a H-bridge made of very large transistors that is switching 600 volts DC, generating a square wave voltage excitation in the series resonance tank that is the primary side of the Tesla coil. The primary side, the primary inductor, and the bank of capacitors that are inside the box here. So the resonance frequency here is around 45 kilohertz. This is a common H-bridge. We need to switch opposite sides. We turn on half cycle B and B switches. We connect this node here, positive voltage here, and here we create negative voltage. So the V out goes negative for half a cycle. And after half a cycle, we switch AA, creating positive here, right? Switching here and switching here and creating negative in this side. So now the voltage reverses and we keep switching. While this happens, a sinusoidal current starts to flow in this tank. It's a series resonant tank, right? It presents low impedance only at one frequency and the current is sinusoidal. But what is the resonance frequency? The resonance frequency will also change because the spark is loading the secondary. So in real time, the frequency characteristics of this multi-resonance tank circuit is changing. How we are going to solve this problem? We can place a fixed frequency oscillator here, or we can create a mechanism to create positive feedback over this resonance circuit here. We have the current here showing to us what is the resonant frequency. Because look at here, in this first step of voltage, we have half a cycle. This resonant tank at a step response will generate half a cycle. So we can use this information, the fact that we have a resonant circuit here, to feed back the information to the driver. And this was the first big idea in the creation of the DRSSTC, was to feed back the current in the primary side to switch the inverter here. So actually what we're gonna do is to add here a current transformer. This current transformer is measuring the current here and feeding back this information to the bridge. And to make it work, this is as simple as creating the correct signals here and feeding back it directly. Yeah, it works very, very well because we have this well-behaved series resonant tank here on the primary. So like if we create, let's say here that we create A and B, this would actually work. So in the start of the burst, the bridge switches one of the sides. The resonant tank is excited by a step response and generates half a cycle. It generates a current profile from the step response of a voltage excitation. Current is negative and it keeps the correct switches in the correct position. When the current reverses here, feedback reverses. When it becomes a little positive here, let's say this is the 0. When it becomes a little positive, feedback switches and it changes the control. Now the voltage goes, I got the wrong color. Now the voltage reverses and now we have a step response in the opposite direction, enhancing even more the energy inside the tank. Feedback is to the correct position, it keeps the voltage, current reverses again, it goes automatically tracking the resonant frequency of the tank. Very, very clever. The initial current here is something like the V peak over the surge impedance, the transmission line impedance of L and C, that is square root of L over C. So the first cycle here has an amplitude that is proportional to the voltage applied and inversely proportional to the surge impedance of the tank. But we already know that if it runs continuously, it's gonna blow out the circuit. After 8 cycles here, we already have 1500 amps on the transistors. So actually we need to finish this burst here. And if the circuits are well tuned, when we are finishing the burst here, all the energy is already transferred to the secondary side and we already have very high voltage on the output capacitance sufficient to break the dielectric condition of the air. So actually the circuit here is a little more complex. It creates A, it creates B, and it receives a signal from the controller that we call interrupter, right? This signal here is a digital logic signal that controls when this burst will initiate and when this burst will end, right? So this comes from an external circuit that people utilizes to control the burst rate, controlling the sound we hear. It begins a burst and it ends a burst. And of course the driver here that is controlling the transistor also has some synchronization logic, like if we have a foul edge of the interruption, the drivers wait to the next transition here to switch in a zero current switching condition. Switching only when the current crosses zero, not turning off the cycle in the middle of a half wave here, preventing cutting these very high current profiles here in the middle. This topology is very clever because it's self-resonant, it keeps track of the resonant frequency as it changes, but it also has a very important aspect. It works in soft switching. Look here, we are always changing the voltage polarity here on the inverter when the current changes direction here. We are always changing at zero current. This is called ZCS. Zero current switching. So we are always switching the state of the bridge when the current is zero or very near to zero in the transitions when it crosses 0 amps. And this reduces substantially the amount of energy dissipated on the switches. This is very important. Here we commonly also have another current transformer that goes to a parallel circuit here, overcurrent protection, or OCD, overcurrent detection. So this is a safety measure. We have a parallel circuit that is detecting the current, and if it goes over a predefined limit like 2000 amps, if this condition is detected, we turn off the system to prevent further damage. Here on this high voltage bus we have big capacitors, bigger than these ones here. I don't have here the capacitors I used in this project, but they were more than double these capacitors here. We have a bank of these big electrolyte capacitors here to provide the energy and all these amps to this little burst. The burst is very short, like 150 microseconds, but we need to have a lot of energy stored here in the DC bus to deliver to the bridge, to deliver to the primary side. So we use very big capacitors here that are always charging, and for each burst they deliver a lot of amps to the circuit. Now what's missing is a way of generating 600 volts DC, and for this I used a PFC boost topology using 4 parallel boosts. So we understood the inverter and we understood the tuned circuit that is here. What's missing here is a way of generating this higher voltage here. And you may ask me why we generate a higher voltage here. Why we are not using the directly rectified input here? Well, we could, and it works. But placing one more box here, we have the opportunity of make an even better impedance matching of the energy profiles. Like these transistors here can support 1200 volts, 1.2 thousand volts. So we have a lot of range here. We can make a switcher, an inverter that switches 600, 800 volts over the primary side here. If we directly use a rectifier, we're gonna have here 300 volts. So see how we are losing opportunity in the transistor, in the inverter. We are losing opportunity of switching more power to the primary side. So having this intermediate step here, we can better match the power profiles to deliver even more power to the Tesla coil, creating even more sparks, even higher sparks, bigger spark. And with a PFC, a power factor corrector, we also create the opportunity to correct the power factor. If we use only rectifiers here, the power factor on the mains is very bad, because we have a lot of power here delivered in bursts and these bigger capacitors here. Like in my Tesla coil, I had two 15,000 microfarad capacitors. Two capacitors bigger than this one here. So imagine the power factor of connecting this to the mains with a rectifier bridge. I draw this picture here for us to understand the advantages of using a PFC. If we have the rectifier, we already know that the power factor is very low if the capacitance is very big. Actually, for any capacitance here, but it gets worse as higher the capacitance is, because the capacitor, the rectifier, will only charge the capacitor in very short peaks of current. The rectifier will conduct when the voltage here in the input is higher than the voltage on the bus here. So this leads to a very high RMS current, an enormous RMS current here, because all the peaks are very, very, very high. The PFC is an electronic circuit that is actually mimicking a resistive load. That's very interesting. It has power conversion electronics here that is using an algorithm or an electronic way of creating artificially a sinusoidal current in the input synchronized with the voltage. So it uses power electronics to take energy from the mains even with very small currents, and it modulates this current to follow the sinusoidal profile. So for the mains here, the power factor is very high because the load looks resistive. This is the magic of a power factor corrector. One of the easiest ways of creating a PFC is using a discontinuous mode boost converter. This seems very complex, but actually is very, very simple and works very well. Discontinuous mode creates a lot of noise, but in the context of a Tesla coil, that is a very big transmitter, 45 kilohertz transmitter, it doesn't matter. Noise doesn't matter much. So I stuck with this topology. The idea here is that we applied a rectified mains directly over the boost input. We won't filter this input here. So imagine that if we have this voltage here being applied to a rectifier, imagine that here we have a rectifier. If this voltage here is applied here in this node here, we are going to have a pulsed voltage here of 300 volts peak that's not filtered because we don't put any capacitor here. The rectifier directly sources the boost converter. Now we have a very interesting property of a discontinuous boost. What means a discontinuous boost? It means that for each cycle of operation, the current in the inductor goes to zero. So the current in the inductor always goes to zero. So imagine that we are applying here. I will erase this, and we are going to apply here on the IGBT. Let's call it control. The control here to the IGBT is a very low Dutch cycle square wave, right? We turn on the IGBT, turn off, turn on, turn off, turn on, turn off. Let's think that this is running at 10 kilohertz. What happens here is that the current in an inductor is proportional to the voltage applied and time. So like if we have constant voltage and we apply a constant voltage over an inductor, the current of the inductor will grow linearly. Current in the inductor is the integral of the voltage over it. If we halve here the voltage, current in the inductor now will grow 2 times slower. So in the time frame of a cycle of the mains, we have a lot of cycles of the boost operation. So actually the current here, when we turn on the IGBT, the current goes up linearly. So current charges the inductor. When we turn off, current charges the output capacitor. Now the inductor discharges. Now we turn it again, but now current will go higher, right? Because in the time frame of the next iteration of the boost, the input voltage is a little higher. And here I'm drawing it very big here, but we have multiple cycles of the IGBT current inside the mains input. So actually, here we have a pulsed waveform that has this sinusoidal shape, right? So for the mains here, the current input is following a resistive profile because it has the same shape. And of course, Now we can add a very little capacitance here, very little capacitance, and a little filtering inductor here. We can add here a smoothing low-pass filter to make these peaks of current, that is the cycle-by-cycle current of the inductor, from the perspective of the mains, we can make it look like this. And this is how it works. So for the PFC, we have a rectifier, low-pass filtering, and a boost converter. And this is the current profiles. In green, we have the current of a discontinuous boost converter, a lot of cycles inside one of the mains half cycle, and as this peak here is automatically proportional to the amplitude, because the law of the inductor, this comes from the electronics, from how an inductor works. Here we don't have any intelligent controlling trying to create this profile. The peaks are higher because the voltage increases. If we filter these peaks with a low-pass filter, we have here in the input a very smooth current that follows the shape of the sinusoidal signal, and the mains power that's looking here to the PFC think that all this circuit here is resistive. We have only one more problem here, guys. We need to be able to deliver a lot of power. This is not a small boost converter. This boost is also made with very big transistors. So what I did here is that I created 4 parallel boosts, each one working in a different phase, 4 phases interleaved. So the mains here looked to a 4 times the switching frequency, becomes much easier to filter. If we have 4 parallel boosts working interleaved, each one working with a main controller here, controlling each switch, if we have 4 interleaved phases, each boost here was running at 10 kilohertz, but the current here on the filter, 40 kilohertz. Look at this, because I interleaved the 4 boosts. And this simplified a lot this filtering here, creating a much more smooth current waveform here on the input. Well guys, I hope you enjoyed this video. If so, subscribe to the channel, give it a thumbs up, and remember that you can support the channel becoming a patron, link in the description. I see you in the next video of All Electronics.